Hello friends, welcome to the course Exploratory Data Analysis for Data Science with R Software. So you can recall that in the last couple of lectures we have discussed various types of graphs and graphical techniques, mainly for the categorical data and attributes. Now in this lecture we will continue with our univariate graphics and plot, and we will try to understand the graphics like a histogram, kernel density and stem leaf plots. So this, for example, whatever is the role of bar diagram in a categorical data, that is the similar role of histogram in the continuous data. So instead of getting into these things, let us try to understand these concepts and try to take some examples to understand what are they trying to interpret and how they can be constructed in the R software. So let us begin our lecture. So first question comes here, what is histogram and why it is construction? So histogram is based on the idea to categorize the data into different groups and plot the bars for each category with height. You can recall that when we understood the concept of frequency distribution, then we had discussed two types of frequency distribution, one for the categorical variable and say another for the continuous variable. In the categorical variable, it was straightforward, but in the case of continuous data, you had to do some more steps to first convert the data into different groups by creating some class intervals, then finding out their frequencies and so on. So in this case, the histogram is based on the frequency table for the continuous data. So it is constructed when the data is continuous. As you can recall, I told you that in the case of bar diagram, the height of the bar is proportional to the absolute or relative frequency, and the width of the bar has no meaning. But in the case of histogram, we also create the bars, but the area of the bars is proportional to the frequency or relative frequency. Now if you try to understand, the area is defined as the width into height, right? So in the case of histogram, the width of the bar matters, and the width of the bars need not necessarily to be the same. Yes, for all practical application, for the sake of convenience, we always try to make we usually prefer to make the bars of the same width. For example, if I say the histogram which look like this of the equal width, and there is another histogram which looks like this, and then say here like this and here like this. It may not be so easy to compare the value. So that is why we prefer the bars of the same width so that the height can be compared to get an idea about the absolute or relative frequencies of different classes. Right. So if you try to recall, in the case of continuous data, we had created the frequency distribution table like this, where we had defined the classes, and classes like A0 to A1, A1 to A2, which were by defining the lower and upper limits of each of the class. So suppose the entire data is being divided into K classes with their respective frequencies F1, F2, Fk respectively, and we also had defined their relative frequency by dividing the frequencies divided by the total number of observations or the total frequency. So N here is total frequency, right? Now we try to create diagram from this data. So first we try to create this class intervals. For example, you can see here it is A0, then I create here A1, then here A2 and so on. Here it is AK. Now I try to make here this type of values here, F1, F2 and so on. Right, these are the frequencies or relative frequencies. Whatever you want to give, you can give it on the y-axis, and then I try to see whatsoever is the frequency or the relative frequency of the class 1. Suppose this is F1, so this is your here F1, and then similarly here if you try to see, this is your here F2, this is the second class between A1 and A2. Similarly, we have the third class between A2 and A3, and suppose its frequency here is say here F3 and so on, right. So this is how we try to make the histogram, right. So if you try to see, if I keep the width to be the same for all the bars, then it is easier for us to compare just by looking at the height of the bars, that whose class has higher frequency and whose classes has got lower frequency, right? Because we are considering the area. The area of each bar is representing the, or is proportional to the frequency or the relative frequency, right? Now, how to create such a histogram in the R software? So, we have the command here hist, H-I-S-T, and inside this X you have to give now the data vector. You don't have to give this frequency, or you don't have to use the table command. So, this will give us the histogram in terms of absolute frequency, and if I use here the option frequency is equal to false, FREQ all in lowercase alphabet equal to false, then this will give us a histogram of data in X data vector with respect to the relative frequencies, right. So, and then there are many other options which can control the different characteristics of the histogram. For example, if you try to take here main, then main will give us the title of the chart. Then we have here breaks. The breaks is a vector giving the break point between the histogram cells, and so on. Then color is used to set the color of the bar. Xlab is used to describe the title on the x-axis. Similarly, xlim, ylim here, they are specified to define the range of the values on the x and y axis respectively, and so on. There are many other options. I request you to please look into the help menu and try to see what are such different options available. In order to explain you that how to create the histogram, let me try to take here a simple example. So, the height of 50 persons in centimeter are recorded here as follows, right? 166 centimeter, 125 centimeter, and so on, and these values are stored in a data vector here, say here height, right. Okay. Now, I try to create here a histogram by giving HIST inside the parenthesis just the data vector. I will repeat again, please don't use table command inside this parenthesis when you are trying to construct the histogram. It is used only when you are trying to deal with the categorical data or the attribute data, as in the case of bar diagram or the pie diagram. So, now you can see here, this is the histogram in which the class intervals have been created automatically, say 120 to 125, 100 to 130, 100 to 135, and so on the x-axis, and on the y-axis it is here the frequency, right, and this title is coming automatically. So, now you can see here this frequency here is say here 5, this frequency here is 2, and the frequency of the third bar is say here 4, and the width of all the bars, this is the same. So, that is why just by looking at the height of the bars, we can conclude about the total or the say this absolute frequency or the relative frequency of different classes, right. And if you want to customize this graph, for example, if you want to give here the title of the graph as height of the person, so then I can use here the command here main, and within double quotes we will write here heights of persons. If I want to change the color of the graph, then I can use here the COL option as green, and you can see that the color of this graph is changed to now green. Then similarly, by using here xlab, you can specify what you want to specify on the x-axis. Suppose I want to specify here height, so I have to give the heights inside the double quote, and the same thing if I want to specify something on the y-axis, I have to give it in the double quotes a number of persons, so it is coming here, right. So, let me try to first show you these things on the R console, and then I will move ahead with more examples. So, this is your height data I have constructed, and now if I try to make it here, say here hist of height. So, you can see here, this is here the histogram, and if you want to customize it, then I simply have to use these commands here, say like as here main, xlab, ylab, color, etc. So, you can see here this title has come, then x and y axis titles have come, color has become green, and so on. So similarly, if I try to take here one more example from the same data set which you know. So let me try to use here the data set painters from the library MAS that you already have used several times. So in this data set, you know that there are 5 variable: composition, drawing, color, expression, which are quantitative, and school is a qualitative variable, so which I have obtained using the command call names. So let me try to use here the data on the expression. So I call this data painters $expression, which is here like this, and I would like to create here a histogram of this expression data. So I will simply write here hist inside the parenthesis the name of the variable, and you get here this type of data. So you can see here it is this data which looks like a discrete. It has been classified into different intervals, and the corresponding frequencies have been plotted here like this. Right, and if you want to see it, then yeah, I have to first upload here the library here, say MAS. So let me try to come here and then see. Yeah, I will say here library MAS, and then I will say here histo of this variable. You can see here it has come out of here like this. Right. So you can see there it is very easy to create such graphics in the R software. Okay, now I come to one more aspect. This is kernel density plots. So what you have seen that when we are trying to create the histogram, the continuous data is artificially categorized. Right. If you take some data, for example, if you try to, instead of this type of graphic, if you have a graphic where the class intervals are here like this, so this data will be like this and so on. So a lot of things in the histogram, they depend on the width of the class interval, and how you have chosen the class width. So in order to avoid this thing, we can also plot kernel density plot, which is a smooth curve, and it represents the data distribution. Right. So this density plots are like say smoothened histogram. For example, if I try to create here a histogram like this one, and if I try to make it here the midpoint of the range, and if I try to join them together by a smooth curve, and here also you can see that if I try to make it here more number of here, see here this narrower bars, then it may look different, right? So if you try to reduce the width of the bar, then the curve will become more smoother. Right. So this smoothness is controlled by a parameter which is called as bandwidth. And density plot actually visualizes the distribution of data over a continuous interval or time period, and it is essentially a variation of histogram that uses kernel smoothing to smoothen the plots by smoothing out the noise or the randomness. Right. The peaks in the density plot, they display where the values are concentrated over the interval, and density plots are better to determine the shape of the distribution than the histogram, because the density plots are not affected by the number of bins, means the number of bars or their width. And these density plots are actually created using the concept of kernel density estimate. This is a non-parametric concept. I am not going into the details, but I just want to show you here that a kernel density plot is produced by the function like this one, f at nx is equal to 1 upon ns, summation I goes from 1 to k of x minus xi upon h is greater than 0, where this n is the sample size, h is here the bandwidth, and k is here the kernel function. And different choices of k provides the different estimates. And yeah, these kernels are not defined arbitrarily, but this satisfies some condition, just like the condition in the case of probability density function. I am not going into that detail, but before I try to give you the idea of this kernel plots, I wanted to give you that things are not coming from sky, but they are based on some statistical concept. If you want, you can study from the book. right. So, for example, if I say this, a rectangular kernel is defined here like this, kx equal to 1 by 2 if x is lying between -1 and 1 and 0 elsewhere. And similarly, there is a panic-Kanico kernel which is defined here as like this, kx is equal to 3 by 4, 1 minus x square if mod of x is less than 1 and 0 elsewhere. And similarly, there is another choice of kernel which is based on the normal distribution, and this is called as Gaussian kernel, which is actually the default kernel used in the R software. And I will show you that if you try to choose different bandwidth and different choices of kernels, then the structure of the density plot gets actually changed, right. So, let me try to take here a simple example to show you the examples on this kernel density plots. So, I have considered here a data set where the heights of 50% in centimeter have been recorded like this, 166 centimeter, 125 centimeter and so on, and these heights have been stored in the data vector here, height, right. Now, I try to create here a density plot. So, the command here is you have to write down here plot plot, then inside the parenthesis density density, and then inside the parenthesis height, the variable in which you have stored the data. So, you can see here that this will look like this type of curve where it is showing that capital N, the total number of observation is equal to 50 and the bandwidth used is 5.397, and here there are the values of the density and so on, right. Now, if you try to compare the histogram of the same data, this data which you have taken here, I have created its histogram, and then I am trying to plot here this kernel density. So, you can see here they are trying to give the similar information, but in a different way. Yeah, the histogram is the widths are actually quite high, that is why it is giving you such values. But you can see here that the maximum value is somewhere here and here also. They are this almost matching. So, it is based on certain concept because the data is smoothened, right. And similarly, if you try to use here the option here actually adjust. So, you can see here what is happening. I am using here the value of parameter adjust ADJUST as 0.5 and 1. So, you can see here when you are trying to use the parameter 0.5, then the curve has more variation like you can see here like this. But if you try to use here a higher value of the parameter adjust, then the curve is becoming more smoother. So, that means if you are trying to increase the value of the adjust, then the curve will become more smoother, and you can see here the bandwidth in the first case when adjust is 0.5 is 2.698, and whereas when you are trying to use the adjust equal to 1, then the bandwidth here is 5.397. So, as you increase the value of the adjust, the value of the bandwidth also increases. Bandwidth means the Gauss width in which you try to make the class intervals, right. Similarly, if you try to take here adjust equal to 2, then and if you try to compare it with adjust equal to 1, you can see here that adjust equal to is much smoother than even adjust equal to 1 and so on. And in this case, when adjust is equal to 2, then the bandwidth is 10.79. And if you try to plot these three figures on the same graphic, then you can see here adjust equal 0.5, 1 and 2. This is how the graphs are changing. They are becoming more smoother, right. And now, if you try to change the kernels, so if you take the same data set and if you use the option here kernel is equal to Gaussian and kernel is equal to rectangular, then you can see for the same data set the structure is more or less same like this here, but they are different, whereas the bandwidth is the same in both the cases. And similarly, if you try to take another kernel, Panic-Kanico and triangular, then you can see here still the structure is similar, but they are different, and whereas the bandwidth remain the same in all the cases, right. So, this is the kernel density plot actually, and let me try to give you this kernel density plot on the R software so that you can understand it. So, this is my here data on here height. And now, I will try to say here plot this here density height. You can see here this is here like this. And if you try to take here, causing the value of here adjust, so you can see here how it is changing. And if you try to make it here adjust equal to here, say here 1, so you can see here it is becoming more smoother. And if you try to make it here adjust equal to here 2, then it is becoming more smoother. And after that, even if you try to take adjust equal to 3, it will become, say, more smoother, but the difference is not that much, right? And similarly, if you try to use here different types of kernels, say if I try to use here the Gaussian, then it is like this. If I try to use here the rectangular kernel, then it is here like this. And if I try to use here, let's say a Panichchenko kernel, it is here like this, it is changing. And if I try to use here this triangular kernel, then it is here like this, right? So you can see here that by choosing different types of kernel also will give us different types of kernel density plots. So now it is up to you that how you want to use them. I have given you all the options, right? Now after this, I come to one more type of graph which is called as stem and leaf plots. So these stem and leaf plots actually show the absolute frequency in different classes, just like the frequency distribution table or a histogram, right? And they also present the same information what a histogram does. And this stem and leaf plot of a quantity variable is a textual graph. The information is given in terms of actually text that you will see that present the data according to their most significant number numeric digits. And actually this is more suitable when you are trying to use the smaller data set. For example, this kernel density plots, they are very useful in data science because usually we are dealing with very big data sets, right? So this stem and leaf plot is actually a sort of tabular presentation where each data value is split into a stem and a leaf. You know that if in a tree it is something like this, you have here, this is here stem and these are here the leaves, right, just like this. Or you can see here this is the stem and then there are here leaves like this one, right. So the stem is the first digit or digits and the leaf is usually the last digit actually. So for example, if I want to write down here 56, then it is split into say 2 letters 5 which is the stem and 6 as the leaf. Similarly, if I am writing here stem as 2 and leaf as here 8, this means this is representing the number 28. So in order to create the stem and leaf plot, what we do, we try to separate each observation into a stem consisting of all but the final, which is the rightmost digit, and the leaf the final digit. Then stem may have as many as digits needed, but each leaf contains only a single digit. And then we write the stem in a vertical column with the smallest at the top and draw a vertical line at the right of this column, on the right hand side of this column. And we write each leaf in a row to the right of the stem in the increasing order out of from this stem, right. So if you try to plot this in our software, then the command here is stem, STEM, and this will produce a stem and leaf plot and the values in the data vector here x. And we use the parameter actually scale to expand the scale of the plot. For example, if I use scale equal to 2, then this will cause the plot to be roughly twice as long as the default values. So for example, if I say stem x, which is the numeric vector data set, scale is equal to 1, this will control the plot length, and width is equal to 80 means which control the desired width of the plot, right. But let me try to take here a very simple example, a small data set to show you that how it looks like and how we can interpret it. So suppose there are 15 lots and from where we have found the number of defective items, right, and they are something like 46, 24, 53, and this data set has been stored in a data vector defective. like this one. Now we try to create here the stem plot. So we use here say stem defective scale is equal to 2. So now you can see here it looks like here this. So if you try to look at the data set here, this is here 18. So now this is coming here as a 1,8. Right. There is here a data set in an increasing order it is coming. So it is coming out here as a 2,4. Similarly, if I try to see about the number, say this 34. 34 is coming here and it is written here 3 and 4. Then there is a number 35 which is again starting with 3. So it is coming here and it is written here with a 3 and here 5. And there is a number here 38 which is written here, say here 8. Right. Similarly, if I go in the reverse the correction to explain you, if you try to look here, this data set, that means there are 4 values 44, 46, 48 and 49 in the data. So let us try to find out here. 46 is here, 44 is here, 48 is here, 49 is here. And similarly, you will see here, this is here the data 53, 54 and 56. So you can see here they are written in in an order where the number of digits on the right hand side are gradually increasing and then decreasing, right, and the number and the values are here increasing. So this is called here actually stem leaf plot. This is your here actually stem and these are here actually leaves, right. So this is how it will look like, and if you try to compare it with this histogram, it will look like this for the same data set. If I try to make here this histogram, so this part will be something like equal to this one, then this 2 and 4, this will be like this 2 and 4. Now you can see here this 3 has 3 value 3, 5, 8. So this is up to this height, and the next value is the highest, which is here 4, 4, 6, 8, 9. And then you have here the fifth value 3, 4, 6. It has 3 values. So this is here, and this is of the same height of this thing. And then you have here 2 values. So it is coming here, and then 7 has only 1 value 73, which is coming over here. Right. So this is how it is actually done. Now let me try to show you these things on the R console. It is very easy to plot actually. So I try to take here this, copy the data set here, say here defective, and let me clear the screen. And now if you try to see here the command here stem defective scale equal to 2, this will come out to be here like this, right. So you can see here that creating such graphics is not difficult at all, but definitely it requires more practice. For example, in the histogram, if you take a data set and if you try to control the width size, then you will see that the structure of the histogram is changing, right. Similarly, in other cases also, if you try to change the data set, it will give you a different type of picture. For example, in the case of this kernel density estimates based plots, like density plots, if you try to change the bandwidth or you try to change the choice of the kernel, you can see that the smoothness is different and the different types of graphics are plotted. But the more important part is that what type of graphics will be there when you try to use the data set in which you are working. And actually this density plots are more useful when you have a large cut of data. They really give you a good outcome. Because in the case of this histogram, the bin widths will become very small also many times, or if the data is equally scattered, then the frequencies will also increase. So my request is that why don't you take a big data set and try to plot the histogram. It will be better that if you try to plot the relative frequency in the histogram and you try to plot the kernel density estimates based plots. try to change different kernels, try to change different bandwidths, and then try to see what is happening. What is happening in the histogram, what is happening in the density estimates. Similarly, stem and leaf, they are very simple, but it is important for you to understand what they are trying to show you. I have shown you the interpretation, but you try to take the data and try to see that whatever you are trying to interpret, is it really available in the data set? So, you please try to take such examples, such a small data set, big data set, and try to execute, try to practice, and I will see you in the next lecture. Till then, goodbye.